In functional analysis and related areas of mathematics, a sequence space is a vector space whose elements are infinite sequences of real or complex numbers. Equivalently, it is a function space whose elements are functions from the natural numbers to the field K of real or complex numbers. The set of all such functions is naturally identified with the set of all possible infinite sequences with elements in K, and can be turned into a vector space under the operations of pointwise addition of functions and pointwise scalar multiplication. All sequence spaces are linear subspaces of this space. Sequence spaces are typically equipped with a norm, or at least the structure of a topological vector space. The most important sequence spaces in analysis are the p-spaces, consisting of the p-power summable sequences, with the p-norm. These are special cases of LP spaces for the counting measure on the set of natural numbers. Other important classes of sequences like convergent sequences or null sequences form sequence spaces, respectively denoted C and C0, with the sup norm. Any sequence space can also be equipped with the topology of pointwise convergence, under which it becomes a special kind of Frechet space called FK space. Definition. Let K denote the field either of real or complex numbers. Denote by knots the set of all sequences of scalars x n n element of n x n element of K. Display style x underscore n underscore n in Math BF n quad x underscore n in Math BF K. This can be turned into a vector space by defining vector addition as x n n element of n plus y n n element of n equals d e f x n plus y n n element of n. Display style x underscore n underscore n in Math BF n plus y underscore n in Math BF n stacra room def equals x underscore n plus y underscore n in Math BF n, and the scalar multiplication as alpha x n n element of n equals alpha x n n element of n. Display style alpha x underscore n in Math BF n equals alpha x underscore n in Math BF n. A sequence space is any linear subspace of knots. Topic P spaces for 0 n x n p infinity display style sum underscore n x underscore n caret p. If p1, then the real valued operation p display style c dot underscore p defined by x p equals n x n p 1 p display style x underscore p equals left sum underscore n x underscore n caret p right caret 1 p defines a norm on P. In fact, P is a complete metric space with respect to this norm, and therefore is a Banach space. If 0d x y equals n x n minus y n P display style d x y equals sum underscore n x underscore n y underscore n caret p. If p equals infinity, then infinity is defined to be the space of all bounded sequences. With respect to the norm x infinity equals sup n x n display style x underscore inf t equals sup underscore n x underscore n, infinity is also a Banach space. Topic C C0 and COO. The space of convergent sequences C is a sequence space. This consists of all X element of not such that lim infinity Xn exists. Since every convergent sequence is bounded, C is a linear subspace of infinity. It is, moreover, a closed subspace with respect to the infinity norm, and so a Banach space in its own right. The subspace of null sequences C0 consists of all sequences whose limit is 0. This is a closed subspace of C, and so again a Banach space. The subspace of eventually zero sequences COO consists of all sequences which have only finitely many non-zero elements. This is not a closed subspace and therefore is not a Banach space with respect to the infinity norm. For example, the sequence Xn where Xn has 1, k for the first n entries and is 0 everywhere else, i.e. Xn equals 1, 1/2 1 n 0 is Cauchy W R T infinity norm but not convergent to a sequence in COO. equals Other sequence spaces equals the space of bounded series, denote by BS, is the space of sequences X for which sup n, I equals 0 n x I, infinity. Display style sup underscore n left vert sum underscore I equals 0 caret n x underscore I right vert. This space, when equipped with the norm X B S equals sup n I equals 0 n x I. Display style X underscore BS equals sup underscore n left vert sum underscore I equals 0 caret n x underscore I right vert is a Banach space isometrically isomorphic to infinity via the linear mapping X n n element of n I equals 0 n x I n element of n. Display style X underscore n underscore n in Math BF n mapsto left sum underscore I equals 0 caret n x underscore I right underscore n in Math BF n. The subspace CS consisting of all convergent series is a subspace that goes over to the space C under this isomorphism. The space phi or C OO display style C underscore OO is defined to be the space of all infinite sequences with only a finite number of non-zero terms, sequences with finite support. This set is dense in many sequence spaces. Topic properties of p-spaces and the space C0. The space 2 is the only p-space that is a Hilbert space, since any norm that is induced by an inner product should satisfy the parallelogram law x plus y p2 plus x minus y p2 equals 2x p2 plus 2y p2. Display style x plus y underscore p caret 2 plus x y underscore p caret 2 equals 2 x underscore p caret 2 plus 2 y underscore p caret 2. Substituting two distinct unit vectors for x and y directly shows that the identity is not true unless p equals 2. Each P is distinct, in that P is a strict subset of S whenever P if 1 Lx y equals nx and yn display style L underscore x y equals sum underscore n x underscore n y underscore n for y in P. Holder's inequality implies that Lux is a bounded linear functional on P, and in fact L x y x q y p display style L underscore x y leq x underscore q y underscore p, so that the operator norm satisfies L x p equals d e f sup y element of p y does not equal 0 L x y y p x q display style L underscore x underscore L caret P caret asterisk stacra room def equals sup underscore y in L caret P y not equals 0 frac L underscore x y y underscore P leq x underscore q. In fact, taking y to be the element of P with yn equals 0 if xn equals 0 xn minus 1 xn q if xn does not equal 0 display style y underscore n equals begin cases 0 and room if x underscore n equals 0 x underscore n caret minus 1 x underscore n caret q and room if x underscore n not equals 0 end cases gives lux y equals x q, so that in fact Lx p equals x q display style L underscore x underscore L caret P caret asterisk equals x underscore q. Conversely, given a bounded linear functional L on P, the sequence defined by xn equals L n lies in Q. Thus the mapping x L x display style x mapsto L underscore x gives an isometry kappa q q p display style kappa underscore q L caret q to L caret p caret asterisk. The map q kappa q p kappa q minus 1 display style L caret q x right arrow kappa underscore q L caret p caret asterisk x right arrow kappa underscore q caret asterisk caret minus 1 obtained by composing kappa p with the inverse of its transpose coincides with the canonical injection of q into its double dual. As a consequence, Q is a reflexive space. By abuse of notation, it is typical to identify Q with the dual of P asterisk. Topic Q. Then reflexivity is understood by the sequence of identifications P asterisk asterisk Q asterisk equals P. The space C0 is defined as the space of all sequences converging to 0, with norm identical to x infinity. It is a closed subspace of infinity, hence a Banach space. The dual of C0 is 1, the dual of 1 is infinity. For the case of natural numbers index set, the P and C0 are separable, with the sole exception of infinity. The dual of infinity is the bar space. The spaces C0 and P for 1P the space 1 has the Schur property. In 1, any sequence that is weakly convergent is also strongly convergent Schur 1921. However, since the weak topology on infinite-dimensional spaces is strictly weaker than the strong topology, there are nets in 1 that are weak convergent but not strong convergent. The P spaces can be embedded into many Banach spaces. The question of whether every infinite-dimensional Banach space contains an isomorph of some P or of C0, was answered negatively by B. S. Cyrilson's construction of Cyrilson space in 1974. The dual statement, that every separable Banach space is linearly isometric to a quotient space of 1, was answered in the affirmative by Banach and Mazur 1933. That is, for every separable Banach space X, there exists a quotient map Q, 1X (Q L caret 1) to X, so that X is isomorphic to 1 Ker Q (L caret 1 Ker Q). In general, Ker Q is not complemented in 1, that is, there does not exist a subspace Y of 1 such that 1 equals Y Ker Q (L caret 1 equals Y O plus Ker Q). In fact, one has uncountably many uncomplemented subspaces that are not isomorphic to one another. For example, take X equals P displaystyle X equals L caret P, since there are uncountably many such X S, and since no P is isomorphic to any other, there are thus uncountably many Ker Q S. Except for the trivial finite-dimensional case, an unusual feature of P is that it is not polynomially reflexive. P spaces are increasing in P for P element of 1 plus infinity display style P in 1 plus inf T. The spaces P display style L caret P are increasing in P display style P, with the inclusion operator being continuous. For 1 PQ plus infinity display style 1 LEQ P, one has FQ FP display style F underscore Q LEQ F underscore P. This follows from defining F equals F F P display style F equals frac F F underscore P for F element of P display style F in L caret P, and noting that F M 1 display style F M LEQ 1 for all M element of N display style M in mathbound N, which can be shown to imply F Q Q 1 display style F underscore Q caret Q LEQ 1. See also LP space, Cyrilson space, beta dual space, Orlick's sequence space.